Hello, I'm Bertrand Ardouin, Managing Director of XMOD Technologies. I'm going to present our test key and test chip design and layout service offering. For more information, contact us at www.xmodtech.com. I will start with a short introduction, then present some success stories and examples, and then detail the specific skills we have at XMOD regarding the test key design, and then finally I will give a short conclusion. XMOD is a service company for the microelectronics industry. We provide service and engineering, consulting, and software. We act as a reservoir company of specific skills dedicated to link IC manufacturers and circuit designers. We provide services on three main areas: on-wafer characterization, compact modeling or SPICE modeling, and test chip design. We can divide test chip design and layout in two main areas. The first one is DC and low frequency test keys. The second one is RF test keys. Regarding DC and low frequency, we need to design test structures for DC and CV characterization. We need also to introduce mismatch test structures when mismatch needs to be characterized, and also some specific test structures for advanced nodes, such as lengths of diffusion, wet proximity effects, and other physical effects occurring in advanced nodes. We can also add some specific test structures for applications such as extreme temperatures, very high temperatures above 200 degrees C, or cryogenic temperatures down to liquid nitrogen operation. And finally, we can also add some specific structures for radiation-hardened devices. On the RF test keys area, of course, we need to add all the test structures which are related to devices in GSG RF test pads. But we need also to design the corresponding de-embedding structures and to ensure that both correspond well to have a smooth de-embedding strategy. We need to add also specific test structures for physical effects determination. This can include substrate coupling or the determination of specific test sheet resistances, self-heating, and other physical effects. And finally, we can also add some structures for on-wafer calibration when this operation is specifically needed. And in the end, there is another area covering both, which is the design of test structures for model validations, and these are typically some small circuit blocks which allow us to compare the measurements and the simulation. XMOD has over 15 years of experience in test chip and test key design, with 15 plus successful test chip design projects accomplished, down to the 55 nanometer node. We have 30 plus consulting projects on test key design and layout. And in the end, we have 50 plus different processes studied down to the 45 CMOS node. This includes bulk silicon, SOI, CD, and 3.5. We have worked for renowned foundries such as TSMC, ST, Infineon, TowerJazz, XFAB, and many others. Our offering covers CMOS, high voltage MOS, BCD, BiCMOS, HBTs, HEMT, and TFT devices. Test chip design also is dedicated to baseband digital, high voltage, analog and mixed signal, and RF and millimeter wave applications. And those are covering MOS, LDMOS, BGTs, HBTs, resistors, capacitors, inductors, MOS and junction varactors or other transmission lines, and basically all the available device types on the technology process. And our test keys are covering PCMs, modeling, STI and wet proximity effects, mismatch, and QA of the models in the end. Here are some success stories and examples of projects we have done in the past. Here this is a test key design for the 55 nanometer node. This is a compact test chip with DC and RF structures, including QA and validation circuit blocks. This is natively metal density compliant. That means that you don't need to run post-processing for the dummy fields or dummy cheesing of the complex process. Those are optimized for the de-embedding strategy. That means the embedding strategy has been thought well before the design of the test keys, and both are perfectly tightly integrated onto the test chips. And finally, those are fully reusable structures. Another example is a complete DC and RF test chip design and layout from concept to fully validated DRC clean layout. This was an outsourcing project from a foundry, and the test chip was designed from scratch for a new 0.13 micron RF SOI process. And this was a tremendous achievement with the track record of a fully functional test chip in only 6 weeks due to very specific schedule constraints of our customer. We have two other examples here on this slide with a 650 volt test chip example for high voltage CMOS, where we have a very wide range of test keys covering core passive devices and MOS transistors, high voltage devices, and also small circuit blocks for model validation in the end. And below, you have also a 0.18 micron BCD test chip example. Here we have a test chip for cryogenic 77 Kelvin applications. This is typically for defense and aerospace applications where very low temperatures are used. This test chip was dedicated to a complete remodeling of an existing process at such temperatures. Another example is a test chip for radiation hardened design. We have built here a test chip with a radiation hardened elementary cells that are typically annular MOS devices in a standard foundry process to withstand irradiative environment. So custom model and turnkey PDK development are based on this new design cells. And finally, this was a project fully approved by a renowned space agency. When designing test chip for advanced nodes, there are some specific effects which need to be taken into account. The first of which is antenna effect of plasma etching issues. With plasma charges during etching of the metal layers, the gate oxide is degraded during etching. The effect is linked to the metal area connected to the MOS gate, so there is a risk for the gate nodes which are not connected to a diode. In modeling test structures, MOS gates are connected to large area metal pads, so we need appropriate countermeasures in the test chip layout. Here are an example of other specific effects occurring in advanced CMOS nodes. For instance, lithographic proximity for poly and diffusions, where you have different etching of the poly layers depending on the environment. You also have some contact-induced stress, which cause some mobility variations and threshold shifts in the final MOS devices. There is, of course, all the mechanical stress, such as STI or SIGI layers, which depends on the length of diffusions with respect to a given gate. And finally, there are the wear proximity effects. All the effects need appropriate test keys to be included on the whole test chip. For advanced processes, that is 65 nanometer and below, the transistor mismatch becomes a significant part of the overall process variations. This might be due to the random dopant fluctuations, body gate granularity, or the line edge roughness. And of course, these effects also need appropriate test key. Here are some examples of very specific skills we have at XMOD. For instance, here you have a high temperature examples with the CMOS process model up to 225 degrees Celsius. And in the end, you have the results of the verification at circuit level, which is here a ring oscillator example, where the oscillation frequency is drawn as a function of the temperatures for the measurements and the simulation with the new design models. When designing some specific circuit blocks for QA and model validation, it's very important to pay attention to the layout. Ring oscillators, for instance, are strongly layout dependent. You have below an example of a layout influence on the oscillation frequency for two different layouts of the same oscillator. The first one is an automatic layout from digital tools place and route on the left, and on the right you have handmade analog layouts. And you can have up to 30% differences in the end between both in oscillating frequency. So it's very important to know what you are doing when you design such verification circuit. Another example of very difficult analog circuit for model validation is a bandgap voltage reference. Whose accuracy is a very stringent test. You have two examples of different layouts or different bandgap voltage references here. And the final measurements and simulation comparisons with respect to the nominal and worst case models, as well as in a range the older initial foundry model. As it can be seen, the situation has been very much improved with the new developed models. RF test structures are one of the most difficult to design, and XMOD has a broad experience in the layout of the RF GSG test structures and all the associated dampening test structures. The RF test key design is very challenging, and the problem is that poorly designed RF structures severely degrade the measurement accuracy. Finally, very high frequency circuit blocks for model validation examples are presented below. On the left, you have a 70 GHz single-stage, single-ended LNA. In the middle, you have a 70 GHz power amplifier. And in the end, you have a simulation with respect to a very high-frequency LNA designed by the Wuppertal University. As can be seen, we have excellent agreement between the measured and simulated circuit data. This brings me to the conclusion. XMOD is the one-stop place for test chip and test key design layout outsourcing. We have turnkey solutions which are cost-effective. We can design a test chip from scratch, directly to DRC clean layouts. We have more than 15 years of experience in this domain and 15 plus successful track records in test chip design for an extremely wide range of processes. We are a reservoir for specialized skills available at any time without non-recurrent engineering costs. Our test structures are optimally model-oriented. The test keys are designed in such a way that they really represent the intrinsic devices and they represent the actual process, how it will appear further in the PDK for the designers, and that's the most important. Thanks for watching and see you soon on our XMOD YouTube channel.